Last time I talked mostly about, well, briefly why we want to do these experiments, but mostly about how do symmetry violations show up in atoms and molecules? Like, what are the observables? What about the structure of atoms and molecules allows us to see things like electric dipole moments or nuclear shift moments or magnetic quadrupole moments, these sort of observables of CP violation in an atom or molecule, which ultimately arise from some beyond standard model, new or at least sort of new physics in the sensitivity ranges that we expect to reach in the foreseeable future. So today I'm going to talk more about experiments, techniques, and approaches. And so this is not going to be a review. I'm not just going to go through each experiment and list all the properties. I want to focus on more like, why are they working with this species? Why are they using this method? What are they going to do in the future? How can you improve it? That sort of thing. And also as a way to introduce some general experimental techniques that are very common in AMO, not just for these types of things, but very, very generally. I won't discuss all ongoing EDM experiments. I would refer you to reviews if you want to see them. I just chose a cross section that gives what I think is a pretty fair representation, fair and broad representation, I hope. So, there we go. Just to remind you, you can find these slides here on my group website. They may already be on the trisep website as well.
Yeah, so I just added the link.
Super, great.
So if you update them, I assume the link stay the same.
Yeah, probably. So there you go. If you want to pull them up and follow along, they're up there. So I'll jump right in. I guess I showed this picture yesterday when people asked, what's the scale of these things? This one's basically the smallest one. Other ones are bigger than this. But they all fit in a room. This is the Mercury EDM experiment, 199 Mercury, which is based out of the University of Washington. And I think this is a good one to start with, both, well, for a number of reasons. It's sort of, in some sense, the most sensitive, like nuclear type EDM experiment. It's very elegant and conceptually simple. It's a fantastic experiment. It's a very sort of famous experiment in this community. And mercury has a reasonably high vapor pressure at room temperature. It's a liquid at room temperature, and some reasonable fraction in equilibrium is in the gas phase. And so you can just have gaseous mercury at reasonable high density in a vapor cell. So this is actually full of mercury vapor, mercury gas atoms. Mercury has a nuclear, this isotope of mercury has a nuclear spin 1/2. So it has potentially a nuclear shift moment. It has a spherical nucleus, so it doesn't have this sort of like beta-3 octopole nuclear enhancement I talked about. The electronic structure, I'll say if this symbol is unfamiliar to you, I'll talk about them a little bit later. But mercury has 2 paired off s electrons as its valence. So it's not in the second column, but it has an basically identical structure to things in the second column of the periodic table. So a filled s orbital where the electrons are paired off, so there's no net electron spin. There's also no electronic orbital angular momentum because they're s orbitals. So in some sense, the electronic cloud around the mercury atom is like super inert and non-interactive. It's very stable, it's very closed, it's very insensitive to everything. Because it has this core penetrating s electron, the electron wave function samples this very heavy nucleus. And so that gives you this large atomic amplification, this sort of internal field amplification effect. You have core penetrating electrons that see the nucleus of the atom, and so if there's a nuclear shift moment, those core penetrating electrons will be sort of mixed up by it and make them observable in the atom. That's something I talked about in detail yesterday, so I won't say it again, but I encourage you to flip back and review if those ideas got lost. So it's a diamagnetic atom. That's one of the reasons why you can just use it in a vapor. So it's in a vapor cell. So it's constantly bumping into other things, bumping into other mercury atoms. They fill it with some inert gases for some technical reason. So these things are constantly bumping into things. But because the nucleus is the actual kind of physics goal, and that's surrounded by this closed shell of electrons, it can bump into things and the nuclear coherence isn't lost. So you get you can get very highly coherent measurements of the nuclear spin in this ensemble. And because of that, yeah, so the only way that this thing interacts with external magnetic fields is through the nucleus, and nuclear magnetic moments are suppressed by roughly the electron-proton mass ratio compared to electron magnetic moments. So it's just very insensitive to everything except the nuclear shift moments. That's handy. Because they're using a vapor cell, they have a very high number of mercury atoms, a large number of mercury atoms. They can get this very long coherence time because the nucleus is very shielded from perturbations. So they get spin coherence time of minutes, meaning if they align all the nuclear spins and start them processing, they will keep their phase for minutes, despite the fact they're constantly bouncing into stuff, which is pretty impressive. And because of that, this combination of things means that their absolute frequency of resolution is extremely good. It's like 0.1 nanohertz. So that's like 1 second. So basically they could detect, 1 revolution every 300 years. So, that's that square root of n enhancement, the large number enhancement, doing multiple experiments simultaneously. So this is a very, very impressive experiment. Because the CP violation comes from the nucleus, it's primarily sensitive to hadronic CP violation. So for example, you can translate this limit into limit on theta QCD, this strong parameter that you've heard about, both from Mariana and in my talk yesterday. It's actually pretty close to the neutron. It's like within a factor of 2 of what the limit is from the neutron. So it's a very sensitive measurement. Of course, this is using this single source assumption. So remember that these atoms and molecules are always sensitive to some combination of different things. This is the limit you get if you assume that all of the CP violation was coming from just this and nothing else. So it's actually, a little more complicated than that. But this is sort of the scale of hadronic physics that this experiment is probing. There's also 2 experiments with xenon, which are similar in many respects. It's a closed shell, gas phase, spin half nucleus. The experimental techniques they use are very different. But they're, a lot of the important features of the atom are very similar. Any questions about this experiment, which I don't work on, but I'll do my best to answer them. Yes.
I guess based on the last bullet point, is there like a big difference between using a noble gas and using like something that's not a noble gas?
Yeah, so one of the nice things about using a noble gas is that because it's like completely and utterly inert, mercury is like fairly inert, but it's not totally inert. Like it will react with things, it'll stick to things. But xenon, the vapor pressure is like really high. Xenon is not a liquid at room temperature, it's a gas at room temperature. So I think generally you can work with like higher number densities, higher volumes, that sort of thing. The trade-off though is that it's less intrinsically sensitive simply because the xenon is much lighter than mercury. So these like sort of core penetrating nuclei, or these electrons that penetrate the nuclear core result in a smaller amplification of the CP violation in terms of the observable atomic signal. But the trade-off is that you may be able to do a more sensitive absolute measurement with xenon because of these advantages of being able to work with like even larger numbers. Good question. Yeah. Any other questions? So there's another experiment which is also similar in many respects, but has some key differences which relate to some other things I'll talk about later. That's the radium EDM experiment. That's based out of Argonne National Lab. And that experiment uses radium, 225 radium, which very similar to mercury, has a nuclear spin of a half. This sort of closed electron shell. It has a very large atomic enhancement, even larger than mercury because radium is even heavier than mercury. And it also has this static octopole deformation. So it has a very deformed, actually I didn't show 225 radium, I showed 224 radium. This picture of the the data showing how funny shaped the nucleus is, which gives this big enhancement of the nuclear symmetry violation. This atom has that. So meaning that the intrinsic sensitivity is around 1,000 times or so higher than mercury, which has this spherical nucleus and does not have this octopole enhancement. So in other words, they both have sort of comparable field amplification, like the electronic structure benefits that they get are similar, but this one has about 1,000 times larger nuclear enhancement. The challenges, though, are that this is radioactive, has about a two-week half-life. And you can't make vapor cells out of it. It doesn't have a high, radium's not a liquid at room temperature, so you can't make these like sort of reasonably high pressure vapor cells, not just for maybe safety, actually probably not a safety, it'd be fine. It's more just like the chemistry doesn't work out for you for radium. So you can't just swap out the mercury with radium in the mercury EDM experiment and get 1,000 times better measurement. That'd be great. So instead what they do is they use the fact that radium is laser coolable, which I will talk more about. So you can cool it and trap it in the gas phase at ultra cold temperatures, meaning sort of microkelvinish, where you can load it into a trap made out of a focused laser in a vacuum chamber and get a super clean environment. So this is basically just, atoms floating in an ultra high vacuum. So you can get really, really good quantum coherence. Turns out the coherence time here is still not as long as the mercury one, but in principle, you could extend it to be even longer. And down the road, you could imagine doing like quantum enhanced metrology, squeezing enhanced metrology, like Mariano was talking about it a little bit, to even sort of beat the standard quantum limit on this, something like this, for which you need really good quantum control, which basically means you need something like this. So I'm gonna say a little bit more about optical forces and laser cooling, because it's basically one of the main ideas behind the AMO, atomic molecular optical field. It's a very powerful tool. The summary is that lasers can be used to apply forces to atoms and molecules, including cooling and trapping forces, which I'll talk about. It's a major driver of atomic molecular optical and quantum information science. So lots of people do. There are people doing this at Triumph. In fact, they have a really. I'll show some pictures of stuff like right here at Triumph later. Here's the idea. Photons have momentum. If you scatter photons off something, you'll impart momentum, and momentum changes is a force. So here's how it works. So I'll think about this both in sort of an energy space picture, but also physical space. So let's say I have an atom moving to the right, and I have a photon moving to the left. The photon has this momentum, atom has this momentum. And let's say the atom starts in the ground state. If this photon is resonant with this transition, so it has the same energy as this splitting, or very close to it, it can be absorbed. So now the photon is gone. Momentum has to be conserved though, so necessarily this atom absorbs the momentum and slows down a little bit by, h over lambda. And then if this excited state spontaneously decays, it will spontaneously re-emit the photon in a random direction. Not truly random, but it won't emit in any preferred direction. And so on average, so it will receive a momentum kick from each single photon, but on average, if you do many, it will not receive a net photon kick from this decay. So after this process is completed, you have on average changed the momentum of the atom by the momentum of the photon, h over lambda. So that's the idea. Any questions about this? So this is just a force though. This is not trapping, this is not cooling, this is just like a push. So how do you turn it into a trapping and cooling? By the way, each one of these slides is like 2 or 3 Nobel Prizes. So this is like lots of, this is decades worth of very clever ideas, summarized very briefly. So here's a clever idea. Here's like a Nobel Prize worthy clever idea. It's a trick called optical molasses, and the idea is you take your atom and you point 2 lasers at it, counter propagating, so like pointing toward each other, and you red detune the lasers. Red detune means that the energy of the laser, the photons, is actually slightly less than the transition. So, okay, now what happens? Let's say the atom starts moving to the left. The atom, lasers Doppler shift, they're waves, they Doppler shift just like sound waves. If you move toward a laser, the frequency of that laser looks higher. And therefore, this laser, the laser coming this way, will be shifted into resonance. This one will be shifted further out of resonance. So what you'll do is you'll start scattering photons from this laser beam. But that will push you this way, because remember, the laser beam has momentum. The photons have momentum going this way. So you'll get a push the other way. So that means, and the same is true if you do the opposite argument and move this way, you'll start getting pushed this way. So in other words, you feel a force which is inversely proportional to the negative of your velocity. But that's a viscous damping force. That's a cooling force. It tends to push you to a 0 velocity state, which is lowering the temperature. That's pretty neat. Ultimately, it won't cool you to 0 temperature. Nothing cools you to 0 temperature. Something has to start not working at some point. Ultimately, the limit here is that this force is given in discrete kicks, discrete kicks from individual photon scatters. And so, you can't sum up discrete kicks to get exactly 0. You'll always end up with an amount of kinetic energy that's basically the amount equivalent to roughly 1 photon kick. But it turns out that that's like microkelvin. That's very, very small. What is that in E? It's like 10 to the minus 11 EV or something. Don't quote me on that. That might not be right, but that's probably approximately right. It's very, very small. Great. By the way, here's another, this bullet point was also a Nobel Prize. It turns out if you just do this in a magnetic field, like a gradient field, a quadrupole field, you can also get trapping. So this is just cooling. This doesn't give you any trapping. This just dissipates velocity. It doesn't have any sort of center. If you add a magnetic field, the magnetic field 0, it turns out, becomes a center for this, and you get cooling and trapping in a particular location. That's really cool. That's ultra cool. So yes.
I'm just wondering, what temperature do you start cooling using this method?
Yeah, great question. It depends a lot on the species. For atoms, you can grab them right out of room temperature. So a common way, it's not the only way, but a common way that you can make these like optical molasses from atoms is especially like alkali atoms, like cesium and rubidium, they actually have some reasonable vapor pressure at room temperature. So you can just basically put a chunk of metal in a glass jar, pump out all the air, wait for a little bit so there's some rubidium vapor, and then shine these in, and you'll start grabbing atoms out of it. And so you can make a laser trap that way. Okay. And that works. It turns out that doesn't give you the sort of coldest, highest density, best magneto-optical traps, but it works. Just because the forces that these apply are very large. I forget what it is in terms of like, it's like many orders of magnitude larger than like G, for example. So like you can accelerate atoms coming out of like a few 1,000-degree oven to a stop in like, this distance. It's very, very strong force. Yeah.
Is the detuning, is that always fixed, or does that change with the atom's velocity as it cools?
That's a great question. That's another, the solution to that problem was another Nobel Prize. That was, so yeah, you're right. So as this thing slows, as the atom slows, the Doppler shift starts to changing. And so now this sort of resonance condition is messed up. So the solution was to add a magnetic field, because these states shift in a magnetic field. So add a magnetic field with a spatial profile that exactly compensates that effect. Yeah. Thanks. See, if only you'd had that idea like 30 years ago, you know, 40 years ago, I forget. Yeah. So these were great. These are very, very common things these days. It's not even uncommon in like an undergraduate physics lab to make like a magneto-optical trap of a laser of an atom. It's very cool. There's a drawback though. Those are usually used as a starting point for measurement for experiments. The experiments don't usually use a magneto-optical, like the trap itself, the magneto-optical trap is usually not suitable for a lot of measurements because it relies on these optical forces, meaning you're constantly scattering photons off the species, you're constantly exciting it and then letting it redecay, which means you're constantly resetting the state that it's in. So this destroys any sort of coherence, quantum coherence, like immediately. There's another solution to that. Also noble. I'll stop saying that because it's getting corny at this point. But this one was actually a pretty recent one. There's a type of trap called an optical dipole trap, which does not rely on photon scattering and which can conserve quantum information and wave functions very well. And it's based on a classical effect, more or less, which is dielectrics are drawn to the maxima of fields. So even, you know, this is a figure from the Feynman lectures that dielectric objects, you know, you induce dipole moments in them, they're pulled, they want to be in a region of higher electric field. So they feel a force towards an electric field maximum. And atoms are dielectric. So we can use this effect, this trick. Atoms are also very quantum, you know, a blob of dielectric goo is maybe not very quantum, but like an atom is very quantum. So you have to be a little more careful about how you do it. But it turns out that if you have a laser that's far red detuned, just meaning that it's very, very far, you know, like 30 or 40% or something from this transition. So meaning like, you know, it's like tens of terahertz or like, it's a laser that's like a different color. Usually it's like very, very far away from being resonant. A laser is an oscillating electric field. And if you're very far from the resonance, if you're very below the natural frequency of the atom, this oscillating field will induce a dipole in the atom, which is always in phase with the oscillating field. And therefore, this induced dipole will want to go to a field maximum, right? Because dipoles want to sort of align with fields. They want to go to where there's a large field. So as long as you're inducing a dipole, which is in phase with this drive, the lower energy state is the one where the electric field is a maximum. And so if you take this laser and you focus it to a point, which you can do simply just by like sending it through a lens, you get a maximum in 3 dimensions at this focus point. Atoms will be drawn to it and they will be trapped there. By the way, if this was blue detuned, this would become an anti-trap, also for sort of classical reasons that when you drive, if you think of atoms as like a harmonic oscillator, when you drive below the resonant frequency, the response is always in phase with the drive. If you drive above the frequency, the response is out of phase with the drive. So now the dipole would be anti-aligned with the electric field, so it wants to go away from large fields. Of course, real atoms are complicated. Atoms are not two-level systems. If you actually want to figure out like what does some laser do to some atom, realistically, you ask Mariana or you look up one of her papers, which is one of her papers is like a reading assignment in the like atomic physics class I teach because it's, you know, surprisingly complicated. But this picture is totally valid. Realistically, the depths of these traps are limited to a few microkelvin, meaning that if you had a gas with a temperature of more than a few microkelvin, just the random thermal motion would give you enough energy to escape the trap. So the traps are very shallow. So usually what people do is you make a magneto-optical trap to cool to, millikelvin or so, and then you dump those cold atoms into a trap like this. Because this is just a conservative trap, there's no cooling. So you take your cold things and then you stick them in here and then they stay. And this is a very, using these ideas it's like a very hot thing, no pun intended, in an AMO these days, because something that a lot of people are working on is, it turns out that you can, if you make this trap small enough, you can just trap single atoms, like deterministically trap single atoms. And if you use, like fancy beam shaping stuff, you can make funky patterns of like individually trapped atoms in a vacuum. So you can control their geometry, you can move them around, you have complete control over, you can cool them to the ground state of the trap, so you can sort of fully write down the complete internal and external wave function of every one of these things with complete control. And people do really neat things like that, like see many body quantum phases and do like quantum information processing and study like strongly correlated quantum many body physics. So this is a very exciting area, but I won't say anything more about this other than these same techniques that like we're interested in for the type of I do, like lots of people are interested in for other things. Oh yeah, so I said these things. Yes, so you can do a lot with them, and these approaches are both very active. So laser cooling and trapping, they let you get to these very low temperatures where you have good quantum coherence. You can trap in these, these non-perturbative optical traps, that don't rely on photon scattering, so they really don't kind of scramble up the wave function. Of course, why not just laser cool everything? I mean, why would you ever work with something that wasn't laser cooled? It's like, well, we'll see. It's actually hard to laser cool lots of things. I said it's an undergrad lab to laser cool like rubidium atoms or something. But for a random thing, it might be either impossible or, a many-person PhD project. So the next experiment, speaking of complicated things that are hard to work with, I will segue to talking about molecules now. And are there any before I transition over to molecules, are there any other questions about this stuff? So molecules, ytterbium fluoride is the first experiment I'll talk about. This is an experiment based out of Imperial College London. They used the 174 isotopolog of YBF. 174 YB has no nuclear spin, so it's not sensitive to any nuclear shift moments or nuclear stuff, but it does have an unpaired electron spin, so it's sensitive to the electron EDM and also this other CP violating electron nucleon interaction that I briefly mentioned. The experiment works. I'll say a little bit more about how this and other beam experiments work later, but it's a pulsed molecular beam that they basically send through some spin precession chamber to look for symmetry violating spin precession in the presence of fields. One of the notable things about this experiment is that it was the first experiment to beat any atomic EDM, or to beat the best atomic EDM experiment, which was with thallium at Berkeley, which did a measurement in 2002. This was their limit, so it's about 100 times less. It's about 100 times larger than the current limit, but this was 11 years ago, so there have been lots of improvements since then. But this was the first result. This experiment it's an active experiment that's being upgraded, and I'll talk more about it later. How they're upgrading it. It's with laser cooling. Laser cooling's hard. Now, I'm not gonna give like a molecular structure and spectroscopy, review, but I just want to talk about a few of the kind of most important features of molecules that make them interesting for symmetry violation searches, and to kind of connect with what we were talking about yesterday. Molecular structure is it's shockingly complicated. So this is from a book that I like to show people if I want to scare them away from using molecules, because equation 3.297 has, 32 subparts because it was too long to fit on one line. This is the Hamiltonian of a diatomic molecule with no nuclear spins and ignoring relativistic effects. So in other words, this is the Hamiltonian for like a simple like model non-existing molecule. It's just like a joke. The whole book is like this. It's a really good book. Like I love this book. It's on my desk, but it's like, you got to know what you're getting into. Luckily, the molecules that we'll look at here actually have a fairly simple structure that are highly analogous to the structure of simple atoms, which is not a coincidence. That's why people work with them. But it also means it's kind of easier to understand what's going on. So we're not actually going to go through these terms. They're too small to read because I just wanted to prove a point. So YBF, let's talk about the structure of YBF. Ytterbium has 2 valence electrons. So it's like mercury and radium. It looks like it's a second column element. It's not actually in the second column, it's in some random middle spot. But it has the same electronic structure, just has 2 valence electrons in an S shell that are paired off. So it's a closed shell atom. Fluorine wants 1 electron to fill a shell. And so if you make like a simple like Lewis dot structure, you'd say, well, there's one of these electrons bonds the fluorine, 1 stays around the ytterbium. And it turns out that's true. Usually this type of corny picture doesn't work very well, but in this case, because these molecules have very unique bonding properties, this really simple picture is actually very accurate. I mean, it's more complicated than that, but it's not that much more complicated than that. So you end up with a single metal-centered S electron. So and here, if you do like a proper, quantum mechanical calculation of the electronics wave function on ytterbium fluoride, it looks like this. It's like a big sort of blob centered mostly around the ytterbium. So we're going to look at this picture again later for a different reason. The ground state looks like a single sort of S-like electron. This other electron is sort of deeply bound in a bonding orbital, so it's basically just gone. The valence electron is really just this one. So it looks like an alkali metal. It looks like a hydrogenic thing in some sense. It kind of just looks like a single valence S electron. And this structure is basically the same for other atoms with an S2 valence bonded to fluorines, like anything in this column. Beryllium, magnesium, calcium, strontium, barium, radium, fluoride, very similar. Ytterbium and mercury have similar valence, even though they're like over here and over here. So these are all very similar. And in case you forgot, I know you all remember your term symbol notation because it's the most important thing in your life. But just in case, so alkali atoms are first column atoms. They just have 1 valence electron in an S shell. They have a single electron which has a spin 1/2 in a spherically symmetric potential. So the good quantum numbers are the spin and the orbital angular momentum, L. And for historical reasons, you write this in this weird notation as like a superscript of 2s plus 1. That's basically how many different spin projections are there. And then for L, you write the orbital angular momentum in the number of quanta, except you do this alphabetical thing where you do like S, then P, then D, ... to mean 0, 1, 2. So the ground state, for example, in these alkali atoms, it's a single atom in an s orbital. It has L equals 0 because it's an s orbital. So you'd say it's a doublet S state. The doublet just means there's like spin up and spin down, and S means there's no angular momentum. The excited state is from exciting that single electron to a p state, a higher energy p state. So now L equals 1. You still just have 1 spin 1/2, so that would be a doublet p state. When you have these types of sort of S-centered metal fluoride things, it's very similar. There's one key difference, which is now the potential isn't spherically symmetric, it's cylindrically symmetric. So that means there's less symmetry, fewer good quantum numbers. So L in molecules, the electronic angular momentum is not a good quantum number anymore. But its projection on the internuclear axis, n hat, that is a good quantum number. The electrostatic forces along the internuclear axis basically kind of force the electron spin to be quantized in that frame, as opposed to the lab frame, whatever that means. So you very similarly write term symbols. You still have this 2s plus 1, except now you write lambda instead of L. Lambda is the projection on the internuclear axis, which can still be 0 or 1 or 2. But now you use capital Greek letters instead of Roman letters. So the ground state, because these things are basically the same, you get like a doublet S instead of or you get a doublet sigma instead of a doublet S. In the excited state, you get a doublet pi instead of a doublet P, etc. So the structure is actually very similar. And if you look at, again, if you look at like orbitals, what do the orbitals for these things look like? They look very similar. So here's like the orbitals for an alkali atom, your usual S, your usual P. If you look at something like, a terbium or calcium or something, fluoride, with this single metal-centered S electron, you get something that looks like this or something that looks like this. Like, they look kind of similar. There's this kind of dimple here, this internuclear axis, which breaks, which lowers the symmetry. But functionally, they're very similar. You have strong optical excitations of a few EV, or like somewhere in the kind of visible to near IR, similar rate of decay lifetimes of maybe 10-ish nanoseconds. So they're actually very similar in many ways. Of course, there's a lot of things that actually, these levels are never just a single level, they're actually a bunch of levels, but I'll talk a little bit about that. I should just remove this note here because molecules, though, they don't just have electronic degrees of freedom. So for example, this doublet sigma electronic state is split by the fact that the molecule vibrates. There's a ladder of vibrational states, which are typically spaced by kind of 10 or so terahertz. Each vibrational state is a ladder of rotational states, which at least for these types of molecules is kind of 10 gigahertz or so rotational frequencies. And then after this, so this is pretty generic, like all molecules do this. All molecules have electronic, vibrational, and rotational structure. Everything after this is like extremely molecule specific, it turns out. But at least the types of molecules that we will look at, the sort of fine and hyperfine structure look like this. Because there's this sort of metal-centered unpaired electron spin, which has a magnetic moment. That magnetic moment interacts with the rotation of the nucleus, or of the molecule, right? The molecular rotation is the nuclei rotating around. Nuclei have a charge. Rotating charges make a magnetic field. That magnetic field interacts with the magnetic moment of the electron and splits each rotational state into two states, depending on the relative orientation of the nuclear rotation and the electron spin. This is called spin rotation coupling, and it's typically around tens of megahertz. So you get a J1 half and a J3 half state sort of split out of this N state. And then each of these states is further split into more states by the fact that the fluorine has a nuclear spin. So it has a nuclear magnetic moment on it, and that interacts with the electron magnetic moment of the electron. So depending on the relative orientation of those two things, this splits further into 4 states. And again, this is just one of, this. So each of these states is actually 4 states, and each of these states is a ladder of these states. So it's very complicated. But these are the kind of things that you have to think about when you're talking about molecules. But one of the upsides of this, which relates to what we talked about yesterday, is that gives you this big enhancement due to close line opposite parity states, making molecules more polarizable. Now to mix, you don't have to mix opposite parity electronic states, which are up here. You just have to mix opposite parity rotational states, which are much closer. So you can polarize molecules in much smaller fields. By the way, you can't use these. These states are not mixed by an electric. You might say, like, ooh, these are really close. That's even better. But all of these states are differentiated by spin reorientations, and spin reorientations don't change the parity of the state. So in this molecule that I've drawn, these are the sort of closest opposite parity states would be like that equals 0 and that equals 1 states. But that's still really great. So YBF, for example, the rotational spacing is about 15 gigahertz. And that means with an applied field of 12 or 13 kilovolts per centimeter, which you can totally do in the lab, It's challenging, but you can do it. You can not quite saturate the sensitivity. You can't quite fully polarize it, but you can get kind of most of the way there, which means that this ytterbium fluoride experiment was able to realize effective fields, effective interaction, effective amplifications of the EDM in their species by around 1,000 times larger than these atom experiments, which is what enabled them to eventually beat the atom experiments, even though they're intrinsically much harder to work with. The fact that you can polarize them highly doesn't just give you more sensitivity. It turns out that that's also really important for rejecting a bunch of systematic errors, some of which I'll talk more about. But so what are the challenges? Like, it's 1,000 times more sensitive than atoms. How come that it's not 1,000 times more sensitive than the atomic experiments? Because molecules are really complicated. They're hard to work with. They're even hard to make. Molecular fluxes, this is a beam experiment. They're sort of shooting a beam through some science chamber. The fluxes are just orders of magnitude smaller than what you can make for atoms. That's just the way it is. I'll say more about that later. Are there any questions about this so far? All right. So the next experiment, which I'll talk about, which is very near and dear to me because I worked on this for my PhD, is the ACME experiment, which uses THO, thorium monoxide. It's a collaboration between Harvard, Chicago, and Northwestern. And it's spin precession. It's a beam experiment like YBF. There are some important differences, which I'll talk about. The experiment is actually done in a metastable electronic state, which decays after a few milliseconds, but it turns out that's about the time it takes to fly through here anyway, so it doesn't really matter. And it's currently the most sensitive EDM, electron EDM limit. So this was the first generation limit, and then the second generation limit. So this is the sort of current, quote unquote, best limit on the electron EDM. This one's also being upgraded, basically more molecules, more efficiency. And they hope to have a 10-fold improvement in the next few years. So how do beam experiments work? Here's the idea. Yeah, I was, inspired by the other speakers to kind of really show, like, what do these things really look like? Like, what are you doing in the lab? Like, what are you measuring? You're measuring something, So what you do is you take a beam of molecules, don't worry about how you make those for now. I'll tell you later. You take a beam of molecules, you shoot them through an electric field. So these are just, transparent electrodes in a capacitor configuration. You put a voltage on them, you get an electric field. You shoot the molecules through the field. When they enter, you have some lasers that put them into a known quantum state, in particular, that align all the electron spins in the same direction, which you can do with polarized lasers, for example. So when the molecules, these lasers are just always on, by the way. You sort of shoot the beam through these lasers that are always on. They come out of the lasers, spin polarized. Now they precess in these electric fields and a magnetic field for the first generation, about a millisecond. So, this 22 centimeters. And then you have some other lasers that read them out. So you scatter polarized light off of these, and that gives you information about the polarization state of the molecule, the spin polarization. You detect the fluorescence, and you reconstruct the signal. I'll say a little bit more about that, but like this, I showed this picture yesterday, but here it is again. Like, this is what these things look like. This isn't on a table, but it's like it's in a room. Like the whole ACME experiment, could fit in this room. That's a person over there, to give you a sense of scale. Like I am taller than this thing, so so it's tiny by like high energy particle physics standards, but by like atomic physics standards, this thing is like gigantic. So we're kind of somewhere in the middle. So how do you measure this spin? What are you really measuring? Like, what does your data look like for this experiment? You're shooting these molecules through these lasers, you're collecting the fluorescence, and the idea is, what you want to know is, what's the direction of the spin? Like, how much does the spin precess? So what you do is you shine polarized laser light, say X polarized, And if you collect the fluorescence, that tells you what sort of fraction of the population is along X by looking at the intensity of the signal. And then if you flip it so that it's Y, and then you collect this, that gives you the fraction of the population that has like Y polarization. And then if you take those two, the S and Y information and basically take, and it form a symmetry out of it, that allows you to reconstruct this angle theta in a way that doesn't depend on the sort of overall population, which is important because in these molecular beams, the population is very unstable. The beam flux is super noisy. We do this in Acme. This is done very quickly. Within a single beam pulse, you rapidly switch back and forth between X, Y, X, Y, X, Y, so that you aren't sensitive to sort of beam pulse to beam pulse fluctuations. Like in a single shot, you can reconstruct this asymmetry and sort of back out the angle of precession, and this slope, for example, lets you resolve things like the velocity dispersion. So this is kind of what the data looks like. It looks like these fluorescence traces. You do a bunch of analysis to reconstruct this asymmetry, which lets you reconstruct the phase angle, and then you look for correlations between that phase angle and like electric fields. I'll say a little bit more about that last part later. But any questions about this so far? Yes.
So, I guess I missed it. You're measuring the X and Y spins for different atoms, or?
It's for the same ensemble of molecules. It's a projective measurement. So the molecules basically, they come in, they have some well-defined spin direction, and then we project that spin onto destructively. So each molecule either projects on the sort of, when we do a measurement, projects along the X or Y direction, but with a probability that's given by, cosine of theta. So all of the molecules, every molecule experiences the same measurement lasers. And then every molecule basically probabilistically either scatters an X or Y photon with a proportionality determined by its angle. Because they're individual, like every molecule is in a well-defined quantum state. So the measurements are always uncertain. They're always going to give you either, when you do a measurement in some basis, you always get an answer exactly in that basis. But the probability of getting, X or Y is given by, the amount of the wave function that's in this direction versus this direction. I don't know if that answers your question, but
yeah, I think it's okay.
Any other questions? So the beam, and so one of the many challenges of working with molecules is the fact that they're just really complicated. Is that almost invariably molecules are free radicals with low vapor pressure. So it means that at like room temperature, they're just all in the solid phase. If you want to turn something into the gas phase, usually the approach is you heat it up and then it vaporizes into a gas. The challenge with molecules is because molecules have all of these internal degrees of freedom like rotation and vibration. If you heat them up, those modes will get excited. And so it's very easy to make a gas with molecules, but it's really hard to make a gas with molecules that are all in the same quantum state. Because you need lots of energy to vaporize them, but then they have to be very cold so that they have no internal excitations. So the workaround, so you just do both. That's the solution. At least for the Acme experiment, the method that we used was this cryogenic buffer gas beam. That's what was in this thing, by the way. This is the beam source. The idea is very simple. Conceptually, you take some small copper box, which is like this big. You fill it with cold helium gas. You inject a sample of hot molecules. Again, it's really easy to make hot molecules. Just vaporize something and molecules come off of it. So molecules are very hot. They come out in a very broad distribution of states with lots of kinetic energy. But then they collide with this cold helium, thermalize with it. And so now they're at say 4 Kelvin or so in the gas phase. And if you do this in an inert environment, like helium or neon, they won't react to anything. And if you poke a hole in this box, they'll spray out as a beam. And then you can shoot that beam towards whatever you want to do with it, like do a spin precession measurement to look for electron EDM or something else. This technique it's pretty versatile. It works for anything. So people, you can make these beams using atoms. People have made cryogenic beams of like large biomolecules. It's a very versatile technique. And the beam you get is colder, slower, and higher flux than basically other methods to make molecular beams. So this is kind of what people use these days. It's also the first step for molecular laser cooling, which I'll talk more about that later. So I said for alkali atoms, you can just grab them out of 300 Kelvin. But for molecules, it turns out the forces you can apply are much smaller. So you have to start with them pretty cold to begin with. If you try to grab them out of 300 Kelvin, it won't work. So if you try to grab them out of like 4 Kelvin, it will. Another important feature of the ACME, not unique to the ACME experiment, but an important one, is the idea of parity doublets, which will come back later. We'll see parity doublets again. Parity doublets are closely spaced states of opposite parity, which based on the discussion earlier and yesterday is a phrase I keep saying a lot. It's very important. Because it allows you to polarize things very efficiently in small fields and get very good sensitivity. Here's what they are and where they come from. There are actually many ways of getting parity doublets, but this is where the parity doublets in the THO molecule come from. States which have non-zero lambda, so remember that's non-zero projection of electronic orbital angular momentum on the internuclear axis. States that have non-zero lambda have these doublets because these states with plus or minus lambda are nominally degenerate. They're sort of time reversals of each other in a sense. So they have to have the same energy, like whether the electron is circulating like this or like this around the internuclear axis, it can't shift the energies. The wave functions, it's basically the azimuthal part of the spherical harmonics. The wave function of something orbiting around an axis, the wave function part for the angle around the axis is always just e to the I angular momentum times phi. That's basically these are the eigenstates of like LZ, the LZ operator, which is just like d by d phi. But these are not parity eigenstates. They don't have a well-defined parity. If you apply the parity operator to one of these, it actually turns into the other state. So they don't have well-defined parity. They're not even or odd under inversion. But we know that in free space, the eigenstates have to be parity eigenstates. In the absence of parity violation, the energy eigenstates have to respect parity symmetry. So the actual parity eigenstates, which are the physical eigenstates of the molecule, are superpositions of these plus lambda minus lambda states, which, since they look like this, is actually just sine and cosine relative to the azimuthal angle, which means they look like this. This is like, this is sine of phi, this is cosine phi, or maybe it's the other way around. So what? Well, now if the molecule is rotating, these two states won't be degenerate anymore, because remember this is the angle looking sort of down the internuclear axis, meaning that the molecule will rotate perpendicular, like say in this direction. These two different eigenstates have different moments of inertia. The electron cloud has a different shape in these two, and so when it starts rotating, the energy of rotation, due to the fact they have different moments of inertia, will be different. You can make a back of the envelope estimate because, like, you don't know exactly how big the wave function is, but it's about a Bohr radius. Everything is about a Bohr radius in atoms and molecules. You know the rotation frequency. You can just make a classical estimate of like what's the energy difference between these, and you'd estimate that it's about 100 kilohertz or so, which is actually very, very close to the right answer. For some molecules, for other molecules, that estimate's way off. But for THO, for example, it's like within a factor of 2 of this or something. It's very, very close. And 100 kilohertz, you should compare that. So meaning that each rotational state in a molecule that has this structure is actually split into a doublet of opposite parity states spaced by about 100 kilohertz. So that's yet another factor of 1,000 smaller than like rotational spacing. It's even more than that. So you can polarize these molecules in like a few volts per centimeter fully. And that's useful. So it's useful for a few reasons. One, it's easier to work with smaller electric fields than big electric fields. Big electric fields are really hard to work with because like everything in the universe has like dielectric constant, not zero. So it's just a pain to work with big electric fields. For these, you only need capacitor plates where you put like 10 volts on them or something. You can fully polarize the molecule given this very tiny parity splitting in a few volts per centimeter. But maybe even better than that is that you can play a really cool trick, which is called an internal comagnetometer. And here's the idea: if you can fully polarize the molecule, it means you can either you can put the molecule in a state where it has its dipole up or its molecular dipole down. These two states are split by some energy which is very easy to resolve with a laser. So you can basically just tell the molecules to go here or go here. And because the internal electric field is correlated with the direction of the dipole of the molecule, these two states have equal and opposite electron EDM shifts. So that allows you to basically look for this EDM without changing any external fields. So remember in the beginning, I said in this ideal experiment, you have to like flip your electric field and then redo the experiment. Here, you don't have to change any of the external fields. You just have to just address a different state in the molecule, and you can do the measurement. And that's a very powerful technique to reject systematic errors, which I'll say a little bit more about later. The reason it's called internal comagnetometry is because lots of experiments like this have what they call a comagnetometer species, which is a species that has basically no EDM sensitivity, but is sensitive to magnetic fields. So it allows you to get like an independent measurement of the magnetic field. Since these things are always sensitive to some sort of magnetic noise. So like for one of the neutron EDM experiments, they mix in like helium-3, or for the thallium EDM experiment, the atomic thallium, they just like mixed atomic sodium in and measured the magnetic precession of the sodium. So it's like an independent way to get magnetic field information. But here you can get it independently because it turns out that there are also states that have like opposite magnetic field sensitivity. So you can use different orientations of the electron spin and the internuclear axis to sense magnetic fields or electric fields or the electron EDM without ever changing any external fields. And the reason that's important is because this picture I showed in the beginning, this doesn't exist in real life. In reality, your fields are tilted. When you reverse them, they change direction, and it messes with the other fields too. And just like, no matter what you do, this is going to happen on some level. And given that modern experiments are looking for electric effects, which are at least 1 million times smaller than the magnetic effects, you have to be very careful, and you end up hitting kind of systematic limitations of like how well can you reverse an electric field or a magnetic field. You can't do it infinitely well. But this internal comagnetometer trick gives you another handle, like a data analysis handle, to subtract away a lot of those effects. So the next step in sort of how do you take the data in an EDM experiment? So you take these fluorescence traces, you reconstruct these asymmetries to get the spin precession, but then the way you back out, like what's the electron EDM, is you look for correlations of the spin precession with different things that you control. The three important ones, there are many, many more than this, but three sort of important ones are the external electric field direction, which that gives you sort of a handle on the internal molecular dipole. The external magnetic field, which basically gives you access, or gives you a handle on the electron spin, because there's a magnetic moment. And then what we call N, this molecular dipole orientation. So that's the, do you do the experiment in this state or this state? Like, do you put the molecules in that state or that state when you're doing it? And we, in the community, we call these switches. There's an E switch, a B switch, and an N switch, and a bunch of other switches too, like a theta switch and a G switch and whatever. And you measure spin precession in various experimental configurations and then look for correlations. So for example, you can build a table of like, what are the different things that give you spin precession in your molecule, and how do they behave under these switches? So for example, the electron EDM, the thing that we want, the electron EDM spin precession should change if you change the external electric field, or if you flip the molecule. I remember you're sort of flipping this internal electric field. So this EDM would precess in the opposite direction. But the electron EDM by itself, the signal, well, it doesn't care if you change the magnetic field. The electron EDM doesn't see the magnetic field. On the other hand, you apply a magnetic field. The spin precession from the applied field doesn't care about the electric field or the molecular dipole. It sort of only cares about the electron spin. And of course, if you change the magnetic field, you'll change the sign of the magnetic precession. So we'd say that, this is a B odd thing. This is an N odd, E odd, B even thing. But then you can keep going, right? You can start applying like imperfections. Like, what's the signature of an imperfection? Like a background magnetic field. Okay, you can shield away the field as well as you can, but it's not going to be zero. It's going to be something. What's the signature of that? Well, the signature of that is because there's some constant static field. It should basically never change. The electron EDM, whether you change N or E or B, that background spin precession is just sort of some constant offset. So that should be even under reversal of these switches. Then you can start going to some dangerous systematics. Maybe the most famous one being leakage current. So you apply, the way you make this electric field is you apply voltages to a capacitor plate. The resistance between these two plates is not infinity. It's really, really high, but it's not infinity. So there's some current that flows from one to the other. And when you flip the voltages, the direction of the current changes. So you get a magnetic field, which changes sign when you change your electric field direction. And that will be odd under electric field, just like the electron EDM. But if you have this N switch, you can change the sign of the EDM without actually changing the voltages in the plates. And so that lets you very robustly isolate this from this. And there are other things too, like V cross E, the fact that these molecules have a finite velocity in an electric field, and therefore there's a magnetic field from the relativistic field transform. And in atom experiments, like the thallium experiment, it basically hit a floor with these things where they just couldn't do any better. But with molecules, you can plow right through this. So this is kind of how the experiments proceed. Any questions? So the last experiment I'll talk about, this one briefly, largely because a lot of the features of this experiment I've kind of already talked about in the context of other ones. This one just sort of combines some subset of those other features with some new ones. Is the hafnium fluoride plus experiment, which is collaboration between Gilla and CU Boulder. They do also spin precession in a molecular ion trap. You heard a little bit about ion traps before. The really nice thing about ion traps is that they're super strong. You can basically trap anything in an ion trap. For these optical traps I was talking about, it only works with things that you can cool to a few millikelvin, which it turns out is not that many things. But you can trap anything in an ion trap. And what the Gilla Boulder crew figured out was a way to do an EDM measurement in an ion trap, which is completely non-trivial because, what do you want? I was talking about, you're looking for these little tiny precessing signals, on top of much larger precession from these, fields. You want the electromagnetic environment to be really quiet, and you want constant static fields with no noise. And here you're having like a gigantic, huge, rapidly rotating electric field. But they figured out a way to make it work. So they use lasers. They trap these molecules in this sort of like rotating electric field. So they're kind of always pushed to the center, so they stay trapped. They do all the control with lasers. So basically, shoot lasers at this to read out. Very similar to ACME, which is in many respects, you sort of scatter lasers off to determine the internal state of the molecule. There's some important procedural differences, but overall, you're shooting lasers at molecules to figure out their quantum state. This experiment has a parity doublet structure, like thorium oxide, very, very similar to it. These things called like lambda doublets or omega doublets. I don't think I said their name earlier. Those things I was talking about are called lambda doublets or omega doublets. That's really important for this experiment because you can't flip the electric field in an ion trap because this thing has a positive charge. So you need a particular sign of the field to push the thing toward the center. If you flip the electric field direction, it'll be expelled out of the trap. And it's not a very useful trap then. So you can't change the electric field direction. So they rely on the fact that you can just flip the molecule inside that electric field. So they make a very clever use of that parity doublet structure. And the main benefit of this approach, in addition to the fact that it's fairly powerful because you can apply it to all sorts of species that don't rely on having some laser cooling structure, is that they get very long coherence times. So the ACME and YVF experiments, these beam experiments, are limited to a few milliseconds of coherence time. But this one, they have seconds, and they have plans to increase that even more. This experiment is also it's an active experiment that's being upgraded, and they aim to improve on not this limit, but on the current limit, which is about 10 times smaller than this one, by another factor of about 10 or so. And I say in the next few years, but it's probably going to be more in the next year or so. They're taking their EDM data right now. So that's very exciting. So now I'm going to shift to talking about the future. Of course, some of the things I already talked about are the future because they're things people are currently upgrading and working on. But I'm going to start kind of just looking in the, basically experiments that don't exist yet, is what I mean by future. But I'll maybe pause for a moment and ask if anyone has any questions about those experiments that we talked about. Right. So this one I've divided into parts. So part one is laser cooling, which we've seen before, and how great it is. But now I'm going to talk about how it's actually hard. It's complicated. The motivation is strong, though. Like I said, these beam experiments, including the current most sensitive EDM experiment, are limited to a measurement time, a coherence time of a few milliseconds. You could extend this by making the beam slower or the interaction region longer. It turns out those are hard-fought wins. But if you can just trap them, just like grab onto them and hold onto them, you could increase this by orders of magnitude, like the Gilla experiment proved already with the ion trap, and the radium experiment in the optical dipole trap. They both have like seconds of coherence time in these species that they've trapped. So that's an area that we can take these types of measurements and hopefully improve them by a lot. But there's this challenge that I mentioned before for neutral species, not for ions. Ions, you can use ion trap. For neutral species, you basically have to use these optical traps that I talked about, and they're shallow. You can only trap things in there that are colder than are sort of millikelvin temperatures. It's just hard to cool things to millikelvin. But as we've seen, laser cooling is a good way to do that. So like, let's laser cool other stuff. Everything I'm going to say is very relevant for atomic. There are atomic EDM, but also other precision measurements like parity violation and beta decay studies and things, which also use laser cooling in sort of highly non-trivial scenarios. But the reason that I'm excited about this, and a lot of other people too, is that if you take some numbers which are individually close to state of the art on their own in at least some system. So meaning that someone's done this, someone has done this, someone's done this. No one's bundled all these things together at the same time, which is a highly non-trivial endeavor. But based on the fact that people can do each of these things individually makes us optimistic that you could trap, you know, 1 million molecules with like a 10-second coherence time, and a molecule, like a heavy molecule with good CP violation sensitivity. And if you averaged it for 1 week, you would access roughly 1,000 TeV energy scales for 1 loop things, or like 50 TeV energy scales for 2 loop things. And so I think that's exciting. It's like, it's a realistic pathway to explore these like incredibly high energy scales. It would be hard to explore another way, again, for this CP violating physics. So how do we do that? Let's laser cool, you know, that thing. Let's laser cool some heavy molecule. So to remind you, the laser cooling, the forces, relies on photon scattering. The problem is in the numbers. You typically need to be able to scatter about 10 to the 5 photons, just because the momentum of a typical visible photon is about 100,000 times smaller than the typical momentum of an atom or molecule, you know, at sort of the temperatures at which you create it. So you need to do this 10,000 times, 100,000 times. And so that's fine. If it's a 2-level system, you can do this forever. But if there's any other state that this excited state can decay to, then it's gone. Because remember, the force comes from cycling photons. So if the species is in this state and you don't have a laser addressing the state, it doesn't feel any force anymore. It just falls, just goes away. So there's an obvious solution to this, which is we'll just add a laser here. This is very common. You almost always need lasers like this, even for sort of simple atoms. You need 1 or maybe 2, and we call this a repump. And so like that's fine. But the problem is, as we saw, molecules are a horrifying mess. And so these excited states can and do decay to a big forest of rotational and vibrational states, especially. This problem, it turns out you can't just solve it by like, okay, it's like, okay, buy 50 lasers, like, you know, in the grand scheme of things, like how much is 50 lasers? Turns out practically you'd need a team of laser engineers to run that, and you know, they're hard to come by. But also it turns out that as you add more repumps, the forces you can apply goes down, and so then you have to add more repumps to get the scattering rate back up. So it's sort of like a losing battle. So if you just pick some random molecule, there's no known realistic way to laser cool it, and that's still true. But for certain molecules, if you're very careful about how you choose them, this can be manageable. Meaning this leakage is to a small enough number of states that you can just plug them one at a time, realistically. So how do you find a molecule like that? It turns out the biggest problem is the vibrational structure. And the reason that vibrational structure poses a big problem is because vibration changes in a molecule undergoing an electronic decay have no selection rules. So meaning that any state can decay down to any state, and they do. And the reason to see why this is the case involves some kind of, you know, interesting 1D quantum mechanics that there's a pretty good intuitive understanding of, which is pretty valid. So electronic states in a molecule, you know, you may have forgotten from your like freshman chemistry class. Each electronic state in a molecule has what's called a potential energy surface. So what's the minimum energy given some spacing between the nuclei? So, you know, set the nuclei at some distance, find the electronic wave functions that minimize the energy, and move the nuclei again, find that state. That's called the potential energy surface. So in other words, what's the electronic energy, assuming that the nuclei are at some distance? That's what a potential energy surface is. And when you change the electronic state by exciting it, you know, you get some different curve because you've changed the electronic structure. It's higher up because you've excited the electron. And you know, molecules, when they're in their ground state, they just sort of sit at this minimum point, And then the vibrational states you can interpret as the sort of excitations in this potential, this 1D potential. Vibrational states are excited states in that 1D potential. And you can see they kind of look like harmonic oscillator states, because these things kind of look like harmonic oscillators, especially at the bottom, near the bottom. So, okay, great. What does that have to do with laser cooling? So there's a handy approximation that you can make called the Born-Oppenheimer approximation, which tells you, or which says that because the electron motion, the time scale of electronic motion, the energy scales of electronic motion are much higher than the vibrational motion, the vibrational energy scales. The electronic transitions are basically instantaneous with regards to the vibrational motion. So in other words, if you have some molecule that's vibrating, and say you're in an excited electronic state and the electron decays down to the ground state, instantaneously the vibration can't respond to that because it's an instantaneous perturbation. So it actually stays in the same vibrational state. The vibrational motion stays the same, not the same state. The vibrational motion stays the same. So the vibrational wave function stays the same. So for example, if you're up here, if you're in the excited state in the ground vibrational state, and now you instantaneously decay, the vibrational state is still in this state here. The wave function looks like this, but now this wave function is in this other potential. So it's not an eigenstate of that potential anymore. So it's not going to go back to the ground state. It's going to end up in each of these states proportional to the wave function overlap. That's the sort of instantaneous perturbation, approximation from quantum mechanics. When you have an instantaneous perturbation, your wave function doesn't change. You just reproject it into the new basis. So the probability that you end up in here or here or here or here is just given by the wave function overlap of this with these different eigenstates squared. These are called the Frank-Condon factors, or FCFs. And as an aside, things like rotational structure or like hyperfine structure, they provide very non-trivial challenges, but it turns out they're solvable. So I'm just going to ignore them. This is sort of a fundamental challenge that you can't cleverly avoid by how you choose the laser polarizations and stuff. But so that's the problem. If you're in this state, when this state decays, you can go down to any of these states, and you do, and you don't have control over it because it's a spontaneous process. Any questions?
What's the time scale of this process?
Yeah, so the excited states, the radiative lifetime is typically, for the types of molecules I'll talk about, like 10, 20, 30 nanoseconds. Yeah. Any other questions? So here's some examples of a bad molecule. It's not a bad molecule. There's nothing wrong with the molecule, but it would be challenging to laser cool. Lithium hydride is not diagonal. What do I mean by diagonal? I mean, if you make a big table of these Frank-Condon factors of, like, where do you start in the excited state, where you end up in the ground state, you would like this matrix to be diagonal, meaning that you never change. Like if you start in I, you can only decay down to I. That would be like a diagonal, transition, we would say. Here's an example of a not diagonal transition. Lithium hydride. The ground state looks like this. The excited state looks like this. The potentials look very, very different. So the wave functions look very, very different. And so they overlap, they all overlap with each other. So if you start in the ground vibrational state of lithium hydride, which has a wave function that looks like this, if you reproject it onto the ground vibrational state, ground vibrational eigenstates, it's just a big mess. They all overlap with each other. And so if you look at the probability of starting here and ending up down here, it looks like this. You end up smeared out over a ton of different vibrational states. And because the spacing of these states is large, like tens of terahertz or something, 10 terahertz, you see the x-axis is wavelength. So it's not like you can just sort of modulate your laser and address all these at once. This laser, a laser that just has peaks at all of these, does not exist. So this means you'd have to buy that laser and that laser and that laser. You just have to buy all these lasers. You know, who's got the time or money for that? Calcium fluoride. So based on this, example, you can perhaps see some intuition that you want the ground and excited potential energy surfaces to be the same. If they were identical, then they would have the same eigenstates. And when you reproject the eigenstates, nothing would happen. Calcium fluoride, which I don't show the potentials just because they look exactly the same, is an example of a molecule that is, diagonal, or at least has diagonal transitions. The wave functions in the ground. So here, green, same as over here. Green is the ground vibrational state and the excited electronic state. Blue are the different eigenstates in the ground state. And you can see they actually overlap really well. Like the 0, 0 overlaps really well, and these all sort of don't overlap because it basically looks like harmonic oscillator wave functions. And so this one, if you make the same chart, it looks like this on a log. This is a log scale. That's important. 97% of the time it doesn't change state. 3% of the time it increases by 1, 0.084% it changes by 2, and exponentially down. So with just a handful of lasers, with 3 lasers, if you drive this transition and this transition and this transition, you can, you have, except for 0.0025% of the time, you'll go back into a state where you have a laser addressing that state. And so you can, with calcium fluoride, you can scatter many, many, many photons. Any questions? How do you find molecules like this? You can just look through charts or something. But there's some intuition. Oh, before I get to the intuition, I'll just say a little bit more about the experiment. So people do this. This is pretty new stuff, though. The first laser cooling and trapping of a molecule only happened in 2014. The first laser cooling and trapping of atoms was in like the 70s and 80s. So it took a long time for molecules to catch up for a number of reasons, mostly just because it's really hard. However, this works. If you sort of plug these leakage channels with just lasers, you can scatter enough photons to stop, trap, and cool molecules to like microkelvin temperatures like atoms. It's still challenging. You need 1 laser per vibrational repump. So you still need lots of lasers, but you need like a reasonable number of lasers. So, here, this is from the first paper where someone laser cooled and trapped a molecule. And these are the lasers they had. They had the laser to address this transition, and then this one to plug V equals 1 leakage, this one to plug V equals 2 leakage, this one to plug V equals 3 leakage. So you only needed 4 lasers. It's a little more complicated than that because, as you know, this state is not a state, but a forest of states. So they had to take each of these lasers, had to have frequency components applied to it through modulation to address all of the substructure. The spin rotation splitting and the fluorine hyperfine splitting. So each laser is actually addressing like all of these transitions with multiple polarizations. So it's still really complicated, but like it worked. And people are getting better at this now. But still only 4 species have been laser cooled and trapped, molecular species, all in the past, several years. This one, which is strontium fluoride, calcium fluoride, yttrium oxide, and calcium hydroxide. So it's decades behind atoms, but because there was like decades worth of tricks from the atom community, most of which are like directly portable into here, this field has advanced, very, very rapidly. And people can do fancy stuff with this now. By the way, these experiments all start with this cryogenic buffer gas beam. So this was sort of one of the important pieces in the puzzle to making these work. And for that reason, I mentioned before that you have to start with them pretty cold to begin with, just because you can't scatter that many photons. So your photon budget is very precious. So you try to cool them as much as you can before laser cooling them. And so this cryogenic cooling works pretty well. So yeah, now how do you find, like, how did people figure out these molecules? Did they just kind of guess? No, there's some good intuition. for like, when can you find this type of structure? In some sense, you need to find a molecule where the valence electron doesn't participate in a chemical bond. Like, what do I mean by that? In other words, whether you excite or de-excite the electron, that potential energy surface doesn't change. The potential energy surface is a property of the bond. So you want something where the chemical bond just doesn't care what state that valence electron is in. So, of course, it's much more complicated than that, but it turns out this is a pretty good picture for building intuition. So here's a bad example. This is kind of like lithium hydride, like calcium oxide. This one doesn't work. Intuitively, it's because all of the electrons are involved in a bond. So anytime you excite any of these electrons, you're changing the bond. And so if you do, this isn't an actual calculation, this is a schematic, but if you did an actual calculation, it would look like this. You'd see that the ground and excited potential energy surfaces like really don't overlap. They look very different. The wave functions really don't overlap because the bond is very sensitive to the state of these electrons that you're exciting. But calcium fluoride, which we saw, that one does work because now, like ytterbium fluoride, there are two valence electrons around the metal. One bonds in the fluorine, so it's just gone. But there's this sort of metal-centered electron just hanging around by the calcium that doesn't really care about what's going on with the rest of the molecule. So if you do, again, this is a schematic, not a proper calculation. Calcium fluoride ground or excited states, overlap very well. The state of this electron does not impact the bond, doesn't change the potential energy surfaces, doesn't change the nuclear vibration, etc. And by the way, this also works if you replace this fluorine with just something else that takes an electron like OH. So like polyatomic things, this also works. That's another sort of area I'll talk about. If you look at a little bit more detail than this, like at some of the quantum mechanics that's going on, we saw this before, just to remind you, you get this metal-centered S electron from your S2 metal, single bond to fluorine, you end up with this like metal-centered doublet sigma state. And what really happens, which one of the few times in life in science where when you dig into the details, everything works out better than your initial guess. When this bond forms, you actually get some hybridization with excited, p-type orbitals. And so the resulting electronic wave function, it's actually not some metal-centered S spherical thing. It's actually something that's pushed away from the bond, so, which is exactly what you want. You want something where I excite this electron and this doesn't care. And it's like, this is how you get that. And so this, earlier I showed this wave function of YBF. Actually, this is CAF. Doesn't matter because they all look the same. There's this dimple here on the electronic wave function where it like avoids the bonding region, which is exactly what you want. So it decouples the electronic excitations and the molecular, like vibrational excitations. I think that's really cool. I think that I didn't come up with all this, by the way, so it's okay for me to like gush about it. Other people figured this out. But it's like, yeah, it's really cool. And it doesn't really matter that this is fluorine. This can be a wide range of things. And this picture still works. Any questions?
One question. So yeah, this intuitive picture looks really cool. However, I think you said that only 4 modules so far have been found useful for having found like diagonal structure for laser cooling. And then, for instance, as I said, like YDF has basically the same structure, and it has the sigma and then this whatever in it. And I was wondering if that particular YBF didn't work, or is there anything that experimentally complicated situation about this?
Yeah, great question. So yeah, why have only 4 been laser cooled and trapped? So those aren't the only 4 that have the structure. Those are the only 4 that have been laser cooled and trapped. And it's because these experiments are still extremely hard. There are a lot of experiments working towards laser cooling and trapping molecules. But also remember, this is all pretty new. And so YBF, for example, they have actually laser cooled YBF.
Oh.
They haven't trapped it. Trapping it is another level of complexity, but they've showed that they can cool it. They've basically cooled the beam. So they didn't stop the beam, but they sort of compressed the beam in the transverse directions using laser cooling. But yeah, these experiments are they're just extremely hard. That's the problem. You know, they're tractable and they're doable, but they're still sort of like, it's like a research frontier, even just like doing this still. So that's why. But within the next few years, so like within the last like 1 year, 2 of those were added, 2 of those species. And in the next like few years, I think you'll see several more, probably like ytterbium fluoride, barium fluoride, probably, strontium hydroxide. So yeah, so there's like, so this, it's basically just a new and very active field, but it's just hard still. Yeah.
Thank you.
Any other questions? And this is good news for CP violation searches, because remember, we want like S or P like nuclear core penetrating electrons, either to sample the weird nuclear shift moment distribution, or to have these like relativistic effects that give you amplifications of the electron EDM. And that's, I mean, look at this thing. It's like, it's a bunch of S and Ps mixed together. So this electronic structure gives you these very good sensitivity, you know, very good amplifications of sensitivity that we want. That's really great, because that means you can combine laser cooling and good CP violation sensitivity. And there are a lot of really good candidates. Many of these, actually most of these that I wrote down are actively being pursued with experiments. The reason that none of these have been laser cooled and trapped yet is mostly because they're all heavy. You know, remember, they have to be heavy to get these relativistic effects. They're all heavier than those molecules I listed. Heavier means that you have to scatter even more photons off of them to stop them, and so it's just even harder. But people are doing it. Some of these have been laser cooled in like 1 or 2 dimensions, not stopped and trapped. So the outlook in it is exciting. So barium, mercury, radium, ytterbium, fluorides, these all have this like doublet sigma unpaired electron structure. So they're good for example, like EDM or MQMs. They're also sensitive to the nuclear shift moment, but it turns out they're more sensitive to these things. There are closed shell molecules. For example, thallium fluoride has a singlet sigma. Singlet means like S equals 0. There's no net spin. The spin's all closed shell, all paired off. But so there's no like EDM sensitivity, but there's nuclear shift moment sensitivity. And all of these species have like large sort of field enhancements. So this is an area where in the next several years, like none of these have happened yet. Like nobody has yet combined like laser cooling and trapping and CP violation sensitive molecules. But like, I think it's a very exciting time, because that's probably gonna happen in the next few years. And start giving these like really big gains. So 3 examples. Again, nobody's done this yet, but there are experiments that are working on this right now. And here's just 3. There are more, including some I'll talk about later and some I won't. Ytterbium fluoride has all these features. And so they're working on, they've laser cooled it. They haven't trapped it yet. So they haven't done this yet. They haven't trapped it, but they've laser cooled it. They've also implemented a lot of other like technical improvements in their experiment. Barium fluoride, NL-EDM collaboration, where they have some tricks they want to play with, like very advanced molecular decelerators. So you start with this beam, you have to stop the beam before you can load it into the trap. It turns out stopping the beam is the hardest part by far. So they're going to do some tricks with electromagnetic deceleration. And then thallium fluoride, which is a shift moment experiment, is one that's underway, and they have very cool sciencey looking chambers like this to look for the thallium nuclear shift moment. So these are all underway. So now I will shift to talking about another area where people are trying to do some new stuff. polyatomic molecules. But before I do that, any questions? Polyatomic, why would you bother? Like if diatomic molecules are a horrible, life-ruining mess, why would you go to even bigger molecules? Because it's fun, that's why. But also because the additional degrees of freedom from this ligand that you stick on your metal actually gives you a lot of control over the structure of the molecule and in very useful ways. So, generally, some of these I'll talk about in detail. You have a lot of control over the electric and magnetic field interactions. You can make very polarizable species generically. Of course, you can also just like stick an interesting species in the ligand. So maybe you're actually interested in studying something about like, hydrogen or carbon, and you can actually use the calcium to sort of read out and control these other species in your end molecule. I don't know. You can tune the frequencies of the rotation and the vibration to match, say, some technology or achieve some scientific goal. And overall, as I've hinted at, the structure is very similar because it relies very heavily, all the sort of laser cooling and CP violation sensitivity really relies on the metal-centered electronic structure. It avoids, the bond of the wave function avoids what's over here. So to first order, it doesn't really matter what's over here. So a lot of what I said is immediately applicable to these things. Overall structure is surprisingly similar. And here's a review if you'd like to learn more about exciting things you can do with polyatomic molecules. You can look at this archive paper. And so they really are similar. So fluorine for these types of doublet, S2 valence metals, fluorine bonds very similarly to OH or CCH or OCH3, or it turns out a bunch of other things. That's not always true. Like fluorine and OH don't usually bond in the same way, but they do in this case to these metals, which is kind of one of their unique features. So, for example, if you do a quantum mechanical calculation of what's the doublet sigma and doublet pi states of CAF versus CaOH, they look exactly the same. They're so similar because the wave function avoids this bonding region. So everything I said that relies on the electronic structure, like laser cooling, CPV sensitivity, the way you do the measurement, they're all very, very similar. So that's good news. So you're adding complexity, but you're not adding so much complexity that it looks totally different. It looks pretty similar, but now you have the ability to engineer other features into it. So, what kind of features? Before I talk about what kind of features, again, this is something that people actually do. And it's still really hard, which is why, there's only one polyatomic molecule that has been laser cooled and trapped. And that was just within the last year. So this is, this stuff's happening. It's going on. It's really complicated. Look at all these lasers that they need, because now you don't just have to plug leakage from one vibrational mode. It's a triatomic. It has 3 vibrational modes. And you have to plug leakage to all of those modes. So they have a lot of lasers. But this is a number of lasers that you can realistically use. So they laser cooled and trapped calcium hydroxide and then loaded it into an optical dipole trap, at microkelvin temperatures. So this stuff is for real. But it's still super non-trivial. You need many distinct, so you need many separate high power, stable, spectrally narrow lasers. And it's just hard. Solid state laser technology is increasingly making this more practical. I think 20 years ago this would have just been no way. But these days you can do it with sort of reasonable lasers that you can buy commercially. So that's great. But again, okay, why? Why would you bother? What do you actually get from a polyatomic? You get a lot, but one of the things that I am especially interested in is polyatomic molecules generically have parity doublets. So you can always find a state in a polyatomic molecule where the rotational states are split into these closely spaced states of opposite parity, meaning that you can polarize them in small fields and do the internal comagnetometer trick. Generically, it's generic because it arises from mechanical modes in the molecule. This lambda and omega doubling I talked about, like in THO, relies on electronic structure. This just relies on the mechanical motion of the thing you bond to it. So you can get that sort of in addition to whatever the properties of the metal give you. It's extremely analogous, like how it arises is almost exactly the same as this like moment of inertia picture from the lambda doubling, except now it's not from the electron motion, it's from, like, for example, the middle nucleus vibrating around the symmetry axis, or if you have like an H3 group, that H3 group can rotate around the symmetry axis. This gives you parity doubling in the exact same way. And the reason that's useful is because, so doublet sigma molecules don't have parity doublets. That's one of the drawbacks of these diatomic molecules I was listing, like YBF or HGF. They're doublet sigma states. They don't have, as I sort of showed on the earlier slide, their closest states of opposite parity are rotational states. They don't have parity doublets. These states do. You can have a doublet sigma electronic state, and then you can get parity doubling from the mechanical motion of the ligand you attach to it. So you can combine laser coolability and parity doublets in a fairly unique way that you can't with a diatomic, at least a diatomic sensitive to CP violation. So you can get these doublets for just anything that you stick on here. So that's hopefully a powerful tool. I will skip over this in the interest of time. I encourage you to, you can read through it later and ask me if you have any questions, but it turns out that you generically get parity doublets whenever you have some angular momentum in the molecule with a non-zero projection on the symmetry axis. It sort of generically gives rise to these parity doublets. So here are just a few examples of polyatomic experiments that are like underway. So this is one I work on. This is actually two experiments I work on. One looking for the electron EDM, one looking for a magnetic quadrupole moment. So combining like laser cooling and photon cycling with this parity doubling. There's a parity violation experiment, which I haven't talked about parity violation at all, but again, a lot of the tools and techniques and ideas for what I've been talking about map immediately onto lots of other things. For parity violation experiment, it turns out tuning the magnetic field interactions is really useful. So there's an experiment underway with MGNC. And then there's an experiment, a family of experiments using polyatomic molecular ions with radioactive nuclei like radium, which is a way to combine sort of the molecular EDM ion trap approach with exotic species like radium that have these very large octupole deformations. There are others as well, including with other metals like protactinium. So YBOH is a molecule that we work with in my lab that combines like all of these features I've been talking about. You can cycle many photons from it. It has this polarizable bending mode, which lowers the symmetry and gives you parity doubling. And ytterbium is neat because it has many stable isotopes of all different nuclear spins. So you can do like an EDM experiment or a shift moment experiment or an MQM experiment, all with just different isotopes of the same species. Polyatomic molecules they actually have a lot of applications outside of symmetry violation, which is what I'm interested in. You saw this figure earlier in Mariana's talk about quantum sensing for dark matter, but there are a lot of cool proposals to do robust qubit encoding and quantum simulation and scalable quantum computing platforms by making use of some of the sort of unique properties of polyatomic molecules. All of these experiments have very similar requirements. You need ultra cold temperatures for good coherence. You need efficient preparation and readout schemes. You need good quantum control. So a lot of the tools that all of these people are developing, we're all kind of using for our own things that we're interested in. But again, this is all a very new, last few years kind of field. Any questions about polyatomic molecules before I move on to saying a little bit more about deformed nuclei? So just to remind you, deformed nuclei, quadrupole and octupole deformations enhance hadronic CP violation. So quadrupole deformations enhance MQMs, octupole deformation enhance nuclear shift moments, and those give you access to CP violation in the hadronic sector, different from like electron EDM searches, things like the strong force CP violation or CP violating nuclear forces, etc. And because you can combine these nuclear enhancements with molecular enhancements, you can get very big enhancements in sensitivity. But a challenge with octupole deformed heavy nuclei is that just, unfortunately, all heavy octupole deformed nuclei are unstable, meaning they all undergo radioactive decay on a wide range of timescales, from infinitely short to up to a few thousand years. So like thorium-229 is like 6,000 years. Radium-225 is like 2 weeks. Some of them are minutes. Like francium is minutes. But it's all long enough to use. You can actually do something. You can do a precision measurement. These all have isotopes which last long enough that you can still do a precision measurement with it. One element which gets a lot of attention is radium, because it's very versatile. The neutral atom, the ion, and a large class of radium-containing molecules can be laser cooled and trapped. So that makes it unique. That's because radium is in the second column. So it has all these features I've been talking about, this like S2 configuration, but it also has this octupole deformation. It's the only thing in that column that has this octupole deformation. So it kind of uniquely combines all of the different stuff I've been talking about. So there are experiments, or at least theoretical interest in, the neutral. I mean, the neutral has already been used in an EDM search at argon. Radium fluoride is laser coolable, and very recently, just in the last couple of years, people actually made and measured. Even just everything with molecules is harder. So even just like measuring like what are the energy levels in this molecule, like people only did that a couple of years ago because it's really hard. Especially the fact that it's radioactive. You can't just buy the stuff. Well, actually you can, but it's hard. So here they just basically made it online, at CERN in his old day. You can assemble radium-containing molecules out of ultra-cold atoms. There's this sort of radium trapped molecular ion thing that I briefly mentioned, and we'll say a little bit more about. Radium, like other things in the column, like strontium and calcium, you can stick all different things on the end and still get a laser coolable molecule. So like, radium is neat. Other things are also neat, but radium is neat too. So a generic question that you might ask is like, okay, so let's start combining some of these things. Like, let's take a radium-containing molecule and stick it in a molecular ion trap, like they did for the hafnium fluoride plus experiment in JILA. Like, that sounds like a great experiment. So let's do it. It's especially good for radioactive things because this technique works not by large numbers, but by long coherence times. It's actually pretty well suited for small quantities of things. Say like very short-lived, radioisotopes. So great, let's do that. But the challenge is radium fluoride plus, for example, doesn't have doubling, any parity doublets. It just has a closed shell, singlet sigma. So, not very useful for the ion trap experiment. But if you stick a polyatomic ligand at the end, then you can engineer the structure of the molecule to match your experimental method.